In this lecture, we talk about the network models. Network models actually are not completely new. It's just a special application of linear programming method. So you will see different types of linear programming models, but all these problems, network problems, are the special applications of LP. So in this session, we start from the learning objectives. Then let's see what is the network model. Then we introduce three types of problems. So transportation problems, transshipment problem, and shortest path problem, and corresponding linear programming models for these types of problems. In the end, we also show you the non-network problems sometimes can also be modeled based on the network idea. So we use a previous linear programming case, Sweatshirt Company, to show how this is working. The learning objectives include, after study this topic, you should be able to explain what a network and a network problem is, identify network optimization problems, model network optimization problems as linear programming models, model simulate non-network problems as network problems. So first, let's see what is network models. So the networks are normally formed by the arcs and nodes. So from the figure 5.1 here, so you can see, so these are arcs, arrowed arcs, and the brown circles are the nodes. So if in the nodes there are any flow out data or goods or items, then any flow out, so this is called supply nodes. If there are any flow in items, then the nodes is the demand nodes. So if, for example, in this graph, all the nodes, including both flow outs and flow in, so that's all these nodes are the transshipment nodes. One example for this type of network can be considered as a logistics network or transportation network. So all the nodes are the physical locations of the warehouses, all the retailer shops or transshipment locations. Then all these arcs are the transportation routes or the driving routes of the vehicles. So the common characteristics of the network models include the decision variables represent flows. So for example, we want to decide how many units of the products should be delivered from one location to another location. So the unit or the quantity of the goods are the flows. So from flow balance constraints, so the network model normally can be categorized as a balanced and unbalanced models. So here the net flow sometimes can be negative, sometimes can be positive. So for balanced constraint, the flow in equals to flow out. So here you can see the net flow can be 0, less than 0, or greater than 0. Then this forms into different types of models, balanced or unbalanced models. And then you have the constraint coefficients, often 0 or 1. So that's actually will be shown in the examples later. It's hard to explain now. So integer values and integer results. So because the network problems normally has a physical meaning or applications, so normally we talk about the units, integer units of the items. The simplest network model we will introduce is a transportation model here. So we use an example from textbook. So therefore it's easy for you to check all the details from your textbook. So this example is an executive furniture company's problem. So now you can see these companies have factories and the warehouses all over the country, states. And then now we decide the problem is the company needs to decide which factory to serve which warehouse and how many units they should provide from one factory to one warehouse. So for example, we have the Evansville. So this is a factory. They may allowed to provide products to Cleveland, to Boston, or to Albuquerque. But then the question is on the arrow is a flow. So how many units it should provide for each of the locations. And similarly, you consider all the other warehouse. So we have the factories. So each factory to all the other warehouses. So we formulate the furniture company's example as a more tidy mathematical network. So this is a typical type of network. So you can see in this network, basically you have the oranges and the destinations, and all the X as a single direction. Just all the items only move from the factories to the warehouses. So in other words, in this network, we have supply sides or supply nodes, and the warehouses are the demand nodes. And there is no constraint about which factory to serve which warehouses. So basically, they are allowed to send the products or furniture to all the factories, from all the factories to all the warehouses. So you can see from this morning's factory to ABC, different warehouses. So similarly for two other factories. In this network, we can see all these arcs, all the arrowed lines are the shipping routes. So it's just a direction from factory to warehouse. So it's not necessarily straight lines. So this depends on how the vehicles drive. And we also have the supply quantities. So in this example, the supplies are 100 units in the first factory, 300 units in the Evansville, and 300 units in the Fort Lauderdale. So these are the three capacity we know about the three supply sets. And then in the demand nodes, we also know these quantities are the demands. So now the question is, in these arrows, we would like to calculate how many units they should move from each factory to each warehouse. So in order to solve this problem, it's necessary to know the costs. So in the network problem or in the transportation problem, normally we're interested in minimize the transportation costs. So you can see the estimated cost from each factory to each warehouse. For example, from Evansville to Boston, the unit transportation cost is $4, and then all the others are also given. Now we have identified the parameters for this problem: supply, demand, and costs. So now the question is to decide how many units to move from each factory to each warehouse. So we define the decision variables here. The simplest way to define is just to define Xij as means the number of the furnitures shipped from factory I to factory G, and I is the index for the factories, G is the index for the warehouses. So you can take two ways to define the variables. You can use numerical values. For example, number 1 shows the factory Des Moines. So number 2 for factory Evansville. Factory 3 is Fort Lauderdale. Similarly for warehouse, we can also use numerical values. In the textbook, they actually use the more wordy type of variables. We use the initials of the locations to show the as the index of the warehouses and the factories. So for example, you can see XDA means the quantity of the desks you delivered from Des Moines factory to the Albuquerque. Oh, sorry, it's Q. So similarly, you find all the other variables. So it's the same. In another case, equals to actually define X11 means the same. So it's completely up to you how to define the decision variables. Of course, if you use numerical values, it's rather easy to extend your model to more locations or larger problems. So next step, we define the objective functions. In this problem, the objective function is to minimize total shipping cost or total transportation costs. So all these coefficients are from the previous transportation cost table, and we just sum up all these transportation costs for each route in the network. In another way, if you use numerical values, then you can directly write a shorter or simpler formula for objective function as a sum up all the coefficients times the decision variables. So it's here it's not new because we have introduced linear programming models. Then this more or less the same as we have always done. So next step, we try to identify or define the constraints. So constraints actually are something different or special in the network models. So in this example, we can see for the first factory, the supply. So here they artificially write the constraint as the minus value. So it's a minus 100 units. That just means to distinguish with the demand or flow in. So this actually called flow out, shows negative value. So here in the false constraint, you see this is a demand related constraint. So this also is a flow in type constraint. So the value is the positive. And at the same time, you can see the coefficient for the supply from one factory to one warehouse actually is also negative values. So minus values times the flow out, minus value times flow out. So you sum them together, then you get the constraints. And do not forget the non-negativity. If you try to solve that, you should also remember its integers. So that's the constraints. So just don't feel disturbed by these minus values. So if you understand that it's just the constraint, or we say it's a supply capacity constraints, then you can definitely use the positive values on the both side. So we can actually change the model to the more straightforward way. So that's what I mentioned. This is a supply capacity constraint. I times -1. So times -1 on both sides, then they become the original constraint showed in the textbook. So that's actually no problem if you write directly this type of constraint. So in this particularly example, we see the total supply is 700 units. Total demand is also 700 units. So that actually shows the total supply equals to total demand. So that's a balanced model. That's how we define if or identify if a network model is balanced or not. So after you have formulated the transportation problem, then you can solve the model. This is actually same as we have done previously for linear programming model. So the only difference is here. You can see you can choose a different setup for your Excel workbook. So in this example, if you list all these decision variables, so on this cell, so you see all the 9 decision variables specifically listed. Then you can reformulate your constraints based on the relationship. So which variable involved for each factory or warehouse. Then you actually get, for example, -1, -1, -1. This is related to the first factory supply constraints, and then the second factory, third factory. So that's let's see the warehouse demand. So these are the warehouses, and you just consider the involved warehouses. So the total flow in. So we're interested in the total flow in for each warehouse. So there are 3 oranges. So oranges. So we have the first factory, second factory, third factory involved to this warehouse. So that's how you define the ones. Then this will help you to recall the common characteristics of network models. So we see the constraints coefficients are often -1 or 1 or 0. So all these empty cells means the coefficients are 0. So I do not write them, but you should know there are 0, -1 or 1 values for the constraint coefficients. So you define all these 6 constraints plus non-negative constraints and integer constraints and minimize the total cost. Then this problem can easily be solved in Excel. So that's one setup. So this is actually one way to solve the network problem in Excel. So we'll just write it as the Excel setup 1. We can also actually solve the model by making a new setup. So here we call it alternative layout for your Excel solver setting up. So this actually, I think, more intuitive. So in this system, you can see there's still no problem for your constraints because you know the unit cost, or we see is a objective function coefficients. Objective function coefficients in this part, and the decision variables are still marked as yellow. So here you can see these are the decision variables, but now the decision variable are modeled in a table. So from this table, you can clearly see the decisions from one factory to one warehouse. So this is actually, for example, XDA or X11. So similarly, all these variables also directly defined in this table. The difference from the previous layout is now you have the flow out, or we see this is a supply capacity constraints in this part, and then you have a demand constant actually in the bottom of this table, decision variable table. So this actually is the demand constraint. So as long as you understand how to calculate the right hand side and the left hand side of the constraints, so there is no problem which layout you are going to use. So furthermore, if you want to make them more clear, so you can define flow balance equations. So you calculate flow out and flow in, and then you know the net flow, and then you can move all these constraints. Add all these constraints. So this is the initial parameter we have about the supply and demand. So this is a solution workbook for the transportation problem, because we have used the Excel solver a lot. So you can also check textbook if you feel something missing. So I just skip all the other details. So this slide shows you the solver parameters or the solutions. So you can also run the Excel workbook. You can download them from Blackboard. So you have an Excel workbook to try. So in the first model problem, I actually consider a balanced model. So we know the total demand equals to total supply, both are 700. So now in this slides, we slightly change the initial problem. So we assume the supply increases to 150 in Des Moines. So in the first factory, the supply capacity is increased to 150 units. So it leads to the supply now is greater than demand. So the total supply is 750, total demand is 700. So in this case, clearly you can see it's possible to satisfy all the demands, but how to allocate or assign the supply capacity to each warehouse is no longer equals constraints. So the constraint become inequalities. So here you can see the flow out. The flow out in the Des Moines should be actually flow out should be greater than minus 150. In other words, I think it's more straightforward to write XDA plus XDB plus XDC. So all the supply to different warehouses should be less than the capacity in this factory. So that's similarly for next one, XEA plus XEB plus XEC, actually less than the capacity in this factory, and XFA plus XFB plus XFC less than 300. So the difference, the change actually, these two sides of constraint actually are exactly equal or same. So only difference is if you times -1 on the left hand side and times -1 in the right hand side of all these inequalities, then you have to change the inequality sign into opposite direction. So that's why we get minus. So that's how you change the constraints. So now, as long as your solution satisfies the new constraints, then they will be feasible and optimal. And another type of unbalanced model is the demand. So the supply is less than demand. Obviously, the demand is higher than supply. Probably we can ignore the equals sign here, more interested in the strict higher. So in this case, we assume the demand in warehouse Albuquerque increases to 350, previous is 300. So now the new demand is 350. The supply constraint in also changes. So now all this constraint is flow in constraints. So for all these warehouses, ABC warehouses, so the demand now is higher than the supply. So it's impossible to satisfy all the demand. So you can only satisfy part of the demand. So in that case, here all the demands constraint is changed into inequalities. Especially the first one, we know the demand to the warehouse A now should be less than 350. So for these two types of unbalanced model, it would be interesting to try in your Excel workbook and see how they will affect your decisions or the solutions. So for the transshipment problem, we use an example of Lopez Customer Outfits company's example. So first we use a network diagram to show the relationships between the facilities. So first let's see the supply sets. So the company has 3 tailor workshop. So the shops, they actually make the outfits, and then they ship all these outfits to the finish set. So in this finish set, they help to further adjust or modify the products to fit the customer's specific requirements, and the customers located mainly in 4 cities. So this is tailor's shop. So now this is a products moving flow showed by the arrowed lines. So from the Albany to Richmond, from Richmond to Dallas, to Albany, to Charlotte, from Charlotte to Dallas. So you can see there are multiple routes from different places. Apart from the supply nodes and the demand nodes, in this network we see also this new type of nodes. This is called transshipment. nodes. So in these nodes, you can see they are both flow in and flow out. And for Charlotte, it's the same, flow in and flow out. So now the question is, you have more decision variables to consider. So how many units you should move from Albany to Richmond, from Richmond to different types of customer cities, and so on. So many different routes in the decision variables. In this network, you also see the supply capacity. So this is supply capacity constraints, or we see it as right hand side. If you remember this flow out, you can always use a minus sign. And for customers, this is a demand constraints. Furthermore, we have the cost parameters here. So you can see the transportation cost from each location to another destination. Of course, it's two types. So there are two types of routes. So from tailor shops to the modification or finishing set, from finishing set to basically customer locations. So these are the parameters we identified for this problem. Now we try to model this problem. First, of course, define the decision variables. Again, you can choose to use numbers as an index of your decision variables. You can also use the initials or the names of the locations. So here, decision variables is xij, which is the number of outfits shipped from location I to location J. And then we have the objective function easily calculated. So minimize the total cost in this network. So you have all the movements from one location to another location, they all costs. So you sum up all these costs together. You can also use a shorter form of the total cost. Again, the challenging part is how to formulate the constraints. So in this problem, if we continue to use the idea of flow in and flow out, so then you can see you have a supply constraints and demand, 3 supply constraints, and 4 demand constraints, just like what we did in the first transportation model. So here we actually have a new model, new constraints. So this 2 is transshipment constraints. So here is demand, supply, and here is a demand. And for the transshipment nodes, then we calculate net flow. So in this transshipment nodes, we know they're both in and out. So you have the total from ABH, so 3 supplies. So this become a flow in for the transshipment nodes, and these are the flow out. So this, if this is a balanced constraint, so this are outfit or customized outfit. So basically, we have a equal constraint. So flow in equals to flow out. So that's how you formulate all the constraints. So now you have 9 different constraints. So it's important to have the transshipment nodes constraint defined. Otherwise, you can see you have a decision variable xac, xar, but it has nothing to do with xcd and rid. So you need to make a connection between all these non-connected decision variables. by the transshipment constraints. So this is the transshipment's Excel solver layout or setting up. So this is a linear programming model. So you just put all the constraints and the objective functions into the Excel and try to solve that. So there's no big challenge here. You should work on that by yourself. One thing I would like to see here is no need to do exactly same layout as in this textbook example. So you could choose the way you understand the best. So in this example, they actually made some simplification and also some complexification. So up to you to work on that. So here I just briefly mention, because the objective function is defined here by sum up all these decision variables tables value and the decision variables and the unit costs. So that's why they add artificial large values to prevent the shipment from indirect routes. So here, if you want to simplify that, you can actually replace this objective function by directly calculate the total cost from tailor's workshop to the shipment nodes plus from the shipment nodes times the cost to your final customer locations. So then you do not need to use these large cost values. So check the textbook, you see more details. So next, let's see the shortest path model. So the shortest path problem is actually broadly used for logistics companies. For example, in this example, a furniture company, Redesign, would like to send the furniture from the factory in the location 1 to the warehouse in the location 6. And they use the vehicles to ship all these or transport the furnitures, all the products. And then the transportation route can be different based on the passes they go through. For example, they can go from the city in the node 1 to the city in the node 2, and then to the city node 4, and then to the city 6. And then the total distance they go through is 100 plus 200 plus 100. So this is 400. And of course, they can also go another route. For example, they go from 1 to 2, then to 3, then to 5, then to 6. Then they go through 100 plus 50 plus 40 plus 100 equals 290 kilometers, for example. Now the question is, in this network, very small network, you already have a lot of different routes to consider. So if you use a linear programming model, that will help you to find directly the shortest path, which give you the shortest distance as a solution. So if you also think about the GPS system, you drive a car and you can you would like to from Aarhus to Berlin, then you can choose different routes probably. Then GPS normally take you the shortest time or shortest distance. So that's a similar type of problems. So in order to model this problem, we first define the decision variables. So we define xij as the flow from the node or from the place I to place G. words. In other words, so xij equals to 1 if the roots I to g is taken in your solution, otherwise is 0. So that's how we define the xij. So that also means if the driver is going to go through the route from the CTI to CTG. So here as we define all the nodes from 1 to 6, but they're not all the routes actually defined. In this case, we will only consider the routes existed in the current network. For example, x12 is defined because root 1, 2 existed. So in another way, x14 actually is not defined because there is no route between the two cities. Similarly, we only define the variables when the routes existed. So next we define the objective function. So now you can see, given the defined decision variables, so that's approximately 6, so 18 decision variables, we minimize the total distance. So here the sum is a total distance from factory to the warehouse. Factory is not 1, warehouse is not 6. And the constraints. So next we identify or construct the constraints. Again, here we have the supply and the flow out, always the flow out or transshipment node or the demand node in the network. So we continue to talk about the constraints. So now you can see we just explain why we need these constraints. For example, if we see constraint 1, so this constraint makes sure that as only one route is selected. So you can see we have the route x12, x13. At the same time, we also consider the route x21 and x31. You may think that's silly if you drive the way back from the node 2 to node 1 and then continue to node 6. But mathematically, we need to consider all the possibilities. So that's possible if the route is bidirectional. So we should consider that. So here I just make sure there is only one route selected among these 4 routes. Again, in the demand, in the constraint 6, so the demand constraint as the same. Make sure for the node 6 there is only one route selected and flow in. Maybe I'll change your color. So for the transshipment node 2, 3, 4, 5, now the constraints are all 0. Because in this shipment, in this transshipment nodes, they are both flow in and flow out. So you choose one route in and one route out. So there is a balanced constraint that equals to net flow of this constraint are 0. So that's also equally to see in the node 2. If you can open your textbook and see the node 2, you can see if you have one route into 2, and then you have 3 possibilities to drive out of city 2 to the city 4, 5, 3, and then you actually need to consider the both directions back and into node 4. In the end, just make sure there's one route in and one route out. So that's the meaning of this constraint. It's the same for the all rest of the nodes. So the shortest path problem basically is rather complicated if you look into all these constraints. So one hint for you is always consider the net flow for each node. So all the constraints calculate the net flow. So the problem is also solved in the Excel. So you can download the Excel solver workbook. To further study the solutions. You can see the layout actually is rather complicated. So all these yellow cells are the decision variables. So these empty cells means there is no root. So not defined, so no root defined. As similar, you can see the distance information also only related to the defined variables. And then the constraint, 6 constraints are net flow calculate here as the left hand side and the right hand side. And use a solver to solve that. Minimize the distance from node 1 to node 6. So far we have introduced the transportation problems, transshipment problems, and the shortest path problems. They actually all the real network problems. So the network actually means kind of physical networks. They are the arcs, nodes, clearly defined. So now we actually extend the network models to the non-network type of problems. So here in this example, the sweatshirt company example, we know the company produces sweatshirts in 3 periods, and then the unit cost, production cost can be calculated here by using the cost per hour times the production time. So you get the production cost per unit. So this actually become unit production cost. Production cost per shirt. And then we know the inventory costs, and the initial inventory, all we write is I0 equals to 0, so no inventory in hands at the beginning of the season. So forecast sales is in the T1, in the T2, and the T3, also given. So now the question is how can we formulate this problem? So if you have done this exercise previously, you probably know how to do that. So today we particularly use this exercise to explain how to use the idea from network models to actually understand and formulate this model. So first, the decision variable for this problem would be the production quantities in each period. And the inventory decisions in each period, we use LT. period T. Now I will explain how the problem can be explained by the network model idea. So now let's think about the start point of the network as a total production. So the company can produce for 3 periods. So the production in the period 1, so you got a P1, and so the flow quantity is from P0 to P1. So in the for period 2, the production is from P0 to P2. Production for the period 3 is from P0 to P3 flow. So this is a production in period 3. So this is a flow is a production in the T production, T equals to 1. So that's how you actually define the total productions. So furthermore, you can see the flow out of P0. So that is the total production. Is actually forecasted demand or the sales. And then for each period, if we see this is a T1, change your color probably. Right. So if this is T1, so this is a T equals 2, so this is T equals to 3, then we can actually separate the period into 2 states. So at the beginning, so you have a flow in, which is a P1, and then you actually flow out, so you sell some of the production to satisfy the demand in the period 1. So you flow out from P1, and then you actually get the net flow out of L1 is inventory in the T1. So here again, inventory in the T2. So inventory, if this continue salvage or something, but this I3 is also defined. Salvage. And then the interesting part is on all these arrows or on these arcs, they actually shows the inventories, the decision variables. So you have P1, L1, P2, L2, P3, L3. Then you can continue to identify the constraints for this problem. So we have the balanced flow constraints. So for example, from P0 to P1, the flow actually the only flow out from P0 into become P1, and then this actually equals to 125. This is sales, satisfy the demand, and the rest will flow into L1. So that's inventory. And again, next from P0 to P2, and then this is a flow in plus the flow from the previous inventory. So it's like a LT minus 1. So this is an inventory from previous period. So this is a production in the current period. L equals to the demand plus the inventory in the current period. So next, similarly, so if you could understand this system, and then we can change all these wordy conceptual formulations into the mathematical formulations. So now we get a sweatshirt company's LP model. So these are the production cost in the objective function. So this is a holding cost in each period. So you have decision variables P1, P2, P3, L1, L2, L3, and the constraints is the first period production minus the inventory equals to the demand, or we can name them as another way. So P1 equals to 150 demand plus the end of period inventory. So similarly, you can write P2 plus L1, so the current production plus the inventory from previous period equals to the demand in the current period plus the end of period inventory. Oh, this is not. So this is similar. So current period production plus the previous period inventory equals to demand plus the end period inventories. So these are the typical production lot sizing model. So this inventory model you probably already see in your inventory lectures. Otherwise, you just understand this as a linear programming model. So it's typically for production decision-making problems. So this, if you have this type of problem, there are the flows in and out over different periods, like inventories and productions. Then this can be easily modeled as a network problem. So the solution for many cases are already given. So you can download the Sweatshirt solutions. So that's no different from any other linear programming models. And you can review the solutions and the models. Hopefully, you can use network models for in the future for the non-network problems. So this is what I want to talk about in this lecture. I have to see the network problems can be very large and challenging. So it was to make some effort, take some time to study on that.